Today's lesson is on RSA encryption. There are two encryption schemes. One is called private key encryption, and one example of that is the Caesar cipher. The modern standard of private key encryption is something called triple DES. For example, if you're using encryption on your Wi-Fi at home, here you've got a private key that both sides know, you as well as the router know, and when you're connecting between your computer and the router, let's say you're using triple DES. The other type of encryption is public key encryption, and the example we're going to be learning about today is RSA. And RSA uses a pair of keys, one that's public that you can give to everybody so that they can encrypt things that are going to be going to you, and the other is private, so that way when they send the message to you that's encrypted with your public key, only you can actually figure out what the message is actually saying. In the real world, we use both RSA and triple DES all the time. RSA is used in order to send the signed certificate that transmits the actual shared key. So, you're actually using RSA to transmit the triple DES key in order to keep your connection encrypted. Triple DES is used for the rest of the connection, and the reason why triple DES is used for it rather than RSA is because triple DES is much faster than RSA is for encryption and also for decryption. Okay, well, the two key things behind RSA is that first we start out by picking two prime numbers, okay, letters P and Q. Okay, so for our examples, we're going to pick nice small numbers, 5 and 7. For our prime numbers. In real life, you're picking very large ones that would have many digits that'd be very difficult to calculate out. But we're using smaller numbers just because it's simpler and easier for us to understand what's going on. So the next step is we're going to calculate, we're going to multiply those two numbers together. We're calculating the number that we're going to use for modulus n, and that number is going to be 35. Okay, so this number 35 is the first part of both our private and our public key. Okay, the product of these primes, again 5 and 7 in this case, is shared publicly. Okay, so that anybody can actually get that one as part of the public key. Okay, the next step in using RSA is that you subtract 1 from each of those prime numbers. So we're taking 5 minus 1 gives us 4, and 7 minus 1 gives us 6. And then we're going to multiply those together, and that's going to give us phi. Okay, so 4 times 6 is going to give us 24. So phi is 24 in this particular case. Okay, now we're going to look at numbers that are 1 greater than multiples of phi. Okay, so if we take a phi, okay, and we add 1 to it, that gives us 25. Okay, if we take 2 phi, which is 48, we add 1 to it, that's going to give us 49. 3 phi, add 1, that's going to give us 73. 4 phi, add 1, that's going to give us 97. 5 phi, we add 1, that's going to give us 121. And let's say we'll go with 6 phi, we add 1 to that, that's going to give us 144. So we're going to use the number 144 plus 1, okay, and we're going to see how many times P goes into that. Well, P goes into 145 29 times. Okay, so the important numbers that we have in our key are 35, which is the product of P and Q. All right, 5 is one of our factors, so 35 is our product. 5 is one of our factors. Okay, 35 again is our product, and 29 is the product of, is our other number that we get because it factors into 145, okay, 5 times. Okay, now in order to actually, in order to decrypt it, we're actually using modulus division. Okay, and I'm just going to explain real quick what modulus division is. Okay, modulus division basically is using the remainder. Okay, and that's why we were kind of working with this 24 plus 1, 48 plus 1, etc. Okay, modulus division is also sometimes called clock arithmetic. Let's say, for example, modulus, the modulus operator. If I write a modulus operator in Python is a percent symbol. So 47% 4 means 4 goes into 47 how many times? Well, 4 times 11 is going to give us 44. Well, what's the remainder then? Well, the remainder is 3. So 47% 4, the number is 3. We don't care how many times 4 goes into 47. All we care about is the remainder, and the remainder of that is 3. Okay, so the modulus very often is used in terms of programming in order to figure out if a number is even or not. If we do n% 2, okay, well, if 2 goes into something evenly, the remainder is going to be 0. So if n% 2 is equal to 0, that means n is going to go ahead and be an even number. If n% 2 is not equal to 0, then obviously then the number must be an odd number. Okay, so how does RSA work? Essentially, okay, we have to break our message up into numbers. Okay, so let's say we're going to simplify this and say the letter C is the third letter of the alphabet, so C is represented by a 3. Okay, the letter A is the first letter of the alphabet, so we represent A as a 1. T is the 20th letter of the alphabet, so we represent T as 20. So what we do is we take each of those numbers, 3, and we raise it to the power of the second part of the key. So we raise it 3 to the 5th power, okay, 1 to the 5th power, and then we do 20 to the 5th power. Well, 3 to the 5th power is going to give us 243. 1 to the 5th gives us 1. Okay, 20 to the 5th gives us 3200000. Now we're going to figure out the remainder of each of those numbers, okay, divided by the first part of the key. So again, 3 to the 5th gives us 243, 1 to the 5th gives us 1, okay, 20 to the 5th gives us 3, 2, and then 1, 2, 3, 4, 5 zeros. So now the next part we have to do is we have to take that number and we do modulus, the remainder. Well, how many times does 35 go into 243? Well, I don't know how many times it goes into it, but 35 goes into 243, but with a remainder of 33. So the remainder is 33. That's what we're going to be sending. Okay. 35 goes into 1 0 times with a remainder of 1, so we get a remainder of 1. 20 is going to go into our 35 is going to go into our big number here. I don't know how many times, but it's going to give us a remainder of 20. So what we're sending over the internet is a 33 and a 1 and then to 20. So that's our encrypted message. That's our ciphertext that we're... So our ciphertext that's being sent over the internet is 33, 1, and 20. Now this, somebody else was sending us, or somebody else on the other end of our connection used my public key, which was 35 and 5, to go ahead and encrypt my message, CAT, C-A-T. When that message is sent back to me, 33, 1, 20, nobody else that sees that message can understand what it means. Okay, only I can actually decrypt the message. In order for me to decrypt the message, I'm going to use my private key, which is the other key, which was 3529, to use the same procedure, okay, in order to actually decrypt the message. Okay, that way I can read the message. When I decrypt it, 33.120, okay, we're going to come back and we're going to see that we're going to get the C, which was a 3, A, which was a 1, and T, which was a 20. So that way we know that it says CAT or CAT. And the concept behind this type of encryption is that prime numbers are very, very difficult to factor out. It's very easy to multiply numbers together, but it's very, very difficult and time-consuming in order to factor it out. If you have very, very large prime numbers, it reaches the point where computers can't actually factor it out quickly enough. Okay, it may take years in order to do so, but if it takes years to figure out what the message, why does anybody care what cat means? Okay, because after several years, it becomes pointless. And periodically, again, we were using very small prime numbers. In this particular case, we were using 5 and and 7, I think. In real life, they use very, very large prime numbers in order to make it difficult to calculate out. And every few years, they have to make those prime numbers larger and larger and larger, because as computers become more and more powerful, it becomes easier to kind of more realistic that a computer might be able to break the key. So we have to go ahead and keep making our keys larger, longer, and longer in order to make it harder for somebody to break the key.